Welcome back to your Module 4. Okay, so in this video, we will be discussing about the Unit 2 and Unit 3. Wherein in Unit 2, we will try to establish the relationship between the load, the shear, and the moment. Okay, so that we can now relate the diagram of the load, shear, and moment. And of course, since in your previous unit, Unit 1, there is still a question hanging there, how to connect the points. If that is a straight line, a curve, or if that is a curve, what will be the opening? Will that open upward or downward? Okay. So in this unit 2, that is what we will be discussing, the relationship of this load, shear, and moment, and then that will determine, okay, the connection or the flow of your diagram. And then in relation to that, we will be discussing the point of zero shear, and then what is that zero moment also. Okay, what is the importance, or what is the meaning of that zero shear and then zero moment in our shear and moment diagram. So in this video, these are your unit learning outcomes for Unit 2 and Unit 3. So first is to establish the relationship between load, shear, and moment. Okay, and then second is to draw the shear and moment diagram using equations and then semi-graphical methods. We discussed actually the preliminary way of drawing the diagram using your equation. Okay, substitute the value of x, our limits, and then plot that one. And then the only question there is how to connect. What are we going to use to connect a straight line, a curve, what type of curve? Okay, and then now together with the since we will now be establishing the relationship of load, the shear, and the moment, then actually by means of the graphing or the values only, we can actually graph directly the shear and moment diagram without passing through the equation or without establishing the equations, and that is the semi-graphical method that we are talking about. And then lastly, to solve for the point of zero shear and then point of inflection, which is actually to be derived from the value of zero moment, okay, or point of zero moment. So okay, so recall the shear is actually the summation of force vertical, and then we will be using the sign convention. We will consider, okay, as I've said, you can consider the left and the right. Okay, you can consider the left and the right part of the figure or the section, but actually we will try to stick. Okay, we will try to stick now on the left side, so that we will only be using one sign convention. So okay, summation of forces there is the forces vertical on the left side of your figure, then that is the shear on the section that we are considering. And then the sign convention, we will be following upwards to be positive. Okay, upwards to be positive shear. And then summation on the moment. Okay, summation of the left or the right. Okay, there are times wherein in moment, establishing the value of moment, especially if we are now using or we are just plotting the shear and moment diagram by means of semi-graphical, we do not need to pass on the shear and moment equation. Then actually we can mix together in establishing the moment, we can mix together the summation of moment on the left side. If in the figure or in the section you have a lesser component of figure on the left side, then it is faster for us to establish the moment or to compute the moment. But if you are going to move on a section wherein the right side has a smaller or lesser components for us to get the summation of moment, then that is also better. But you need to consider that in left side, we will stick to the sign convention clockwise is positive. On the left side, we will be following the sign convention clockwise is positive. But on the right side, we will just reverse that one, wherein counterclockwise is the positive. Okay. So again, there will be times we can use these two. But in summation of forces vertical, it will be simpler for us to focus on the left side, since that is the summation of forces vertical. But you can still use the right side if you want. So sign convention for the left side, if we are using the left side, okay, clockwise is positive, counterclockwise for the right side. Okay, or upward forces. Okay, if we say upward, Isn't it, if you are considering the left side, upward forces will make it clockwise, okay? We'll have a moment clockwise, so that's a positive. In your right side figure, or in your upward forces will also make it counterclockwise, which is positive. So simply in the right and left side, you can consider the right side or left side, the upward forces will still be positive moment, okay? Will create a positive bending moment. But of course, in the case that you will have there a load which is a couple or a moment, then okay, do not forget that clockwise in the left side is positive, on the right side counterclockwise is positive, okay? So relationship between load, shear, and moment diagram. So you can read about this, but let's just focus on the figure if you want, okay? You can read about this in your copy. So looking at this figure, we have here a loading, okay? We have here, let's assume a loading here, wherein that loading is going up, or that is a, since again, let's assume that positive is going up for forces. Okay, so let's assume a loading which is a positive loading, and that is of course distributed loading. And then let's try to consider here a small, very small change in length, or let's just consider a, what we call this one, differential length of the beam. Okay, so that is a small length, dx. Okay, so let's say x is the horizontal distance, then that is a small distance x. Then we will be considering there is small loading, which is a w. So if that is now, even if that's a different values of w, since we are considering here very small distance, then we can simplify it as the same values of w, since that is just a very small, okay? And then at a certain section x here, there is a shear v and a moment, okay? Shear and then a moment. However, we will now try to move a little bit with your distance dx. There will be additional small, okay, that d means again derivative, and going back to your differential, the derivative of a certain quantity means a small part, okay? It is a very small part of that quantity. So now within a distance x, we will try to move a little bit within a distance dx, okay? Small dx, or a small distance x. Let's just move a little bit. So there will be additional shear with the original shear in that section at x, and then the original moment. There will now be additional shear and then additional moment, which are very small due to that very small movement that we did, okay? So now your new shear due to that small distance that we adjusted will be v plus dv. Again, dv is this the small additional shear, and then the moment will be m plus dm, okay? We will be using this to establish now the relationship between the load, the shear, and the moment. Focus on this figure. So again, you can read about this. So if we will try to summate moment at this point O, there will be no moment for this v plus dv. What we will be having is a moment of this v, the m plus dm, and then of course your loading w on top. So if we will try to do that, let's assume that clockwise is positive, okay? Clockwise is positive. Your m here is positive, okay? We do not need a distance there since that is a moment. Your moment here is a counterclockwise, so that is a negative m, so minus m, and then minus dm. Okay, by the way, I can actually erase that grouping sign since I already distributed the minus. Okay, so that is just a typo error. Okay, so that is minus m dm, since that is a counterclockwise, all of that m plus dm. And then of course the moment of your v here with respect to O, so that is clockwise, and the distance is dx, so v times the moment arm dx. And then of course do not forget the moment of your load here, since again that is very small. Let's assume that that is uniform, okay? So what is the concentrated of that? W times dx to convert that into a concentrated load, and then multiply to the moment arm dx over 2, or 1/2 of that distance. And then simplifying, of course, that will go negative m, cancels with your m here. We are left with negative dm, that will go on the other side of the equal sign. Equate that one to 0 to make it equilibrium. So that negative dm will go positive on the other side. So we are left here with v dx, w dx, or w, okay, w over 2, 1/2, and then dx, so that is dx squared. However, okay, look at this. Dx is a very small number. Very small number. Then we are going to square that one, multiply that one to itself, then it will make it very small, so it will be negligible. So even if you have here a value for w, that is almost 0, so that will make it negligible. Okay, it will not affect much of the value of this bdx. Therefore, we can simplify that, since again this is applying calculus. So again, let's try to approach that x as almost 0, so it will make this one 0. So you are left with the equation dm is equal to v dx. So now, if you will try to rearrange, okay, that dx divide both sides by dx, your v is equal to dm dx. What does that mean? Your m is the moment. Moment, if that is the equation, then that is the moment equation. Then the first derivative of that with respect to x, that is the meaning of that, okay? Derivative of m with respect to x is your shear. So that's the relationship of a moment and shear, okay? Or in the other words, what is the first derivative? Again, going back to your differential calculus, the first derivative is the slope. Okay? So, what does that mean? The first derivative of m, or the slope of m, is actually your shear, okay, or the value of the shear. Or simplifying this further, for us to relate, or for us to have established another relationship. So this is referring to the relationship of the slope of the moment and the shear, okay? Now, if we will try to go back in this equation here, integrate both sides, or integrate that one. So let's say the moment in the first point is m1, on the second point is m2. The distance on the first point is x1, second point is x2. Then integrating this one using definite integral, okay? So we will not be having that constant of integration c. You will have here m. Integral of this is m. From m1 to m2, so that will be m2 minus m1. Okay, substitute your upper limit, lower limit. And then integrate this one. V is a constant, factor that outside, integrate dx, that will be x from x1 to x2. So substitute upper limit, lower limit. Okay, typo again. What does that mean? Okay, so v x1 minus x times x1 minus x2. So m2 minus m1 is actually the change of moment from first point to the second point. Now, if we will try to look on the other side of the equation, if I will multiply the v, okay, v, and then the change of x1 to x2, x1, x2, x1 minus x2 is the distance between the 2 points, isn't it? So the distance between the 2 points times the magnitude of v. So going back to the examples of the shear and the shear diagram, isn't it that v there is the y coordinate, and then the x is the x coordinate? So x2m minus x1 is a distance x, and then v is a vertical distance, which is actually referring to the dimension of the shear diagram within these 2 points, point 1 and point 2 that we are considering. So, multiplying the distance change in x, or x1 minus x2, times the height v is the area of the shear diagram. So, what does that mean? From point 1 to point 2, the change in the moment from point 1 to point 2 is actually the area of the shear diagram between the point 1 and point 2. So that is the other relationship that we established based on the relationship that we derived a while ago. Okay? So again, slope of the moment diagram is, okay, slope of that, or the first derivative of that, is the shear. Okay? The value of the shear at a certain point. Now, the change in moment from first point to a second point is the area of the shear. Okay, we will be using that to draw the shear and moment diagram without establishing the moment and shear equation. Okay, so that is now to be used on your semi-graphical method. Okay, one more thing is to relate your loading with the shear and the moment. Okay, so now we are done with submitting moment. Now let's try, in this still the same figure, let's try to submit forces vertical. Okay, forces vertical. So what are the forces vertical? Your v plus dv, and then of course your w here. So going up is positive, so w dx times the distance dx. V is going up, and then v dv is a negative. So v and v will be, if I will distribute the negative, will cancel out. This will be a negative dv. It will go positive on the other side. So dv is simply equals to w dx. So the same thing happens just like a while ago. cross multiply dx below or divide both sides by dx, you will have the w, or that is the value of the loading at the certain point, is equal to the first derivative of the shear equation, or that is the slope of the shear diagram. Okay. Now do the same thing just like a while ago, integrate. So integrate of dv and then w dx. So v1, v2, x1, x2, since w is a constant, then this will be v2 minus v1, or that is a change in the shear. And then w, factor that out, that is a constant. Integrate this will be x from x1 to x2. So that is again, this should be, now your change in velocity is equal to the w, that is your force on the top, okay, times the change in x, that is a distance. So again, what is that w? That is the vertical, okay, that is the vertical dimension of the load that we are if we are considering from 1 to 2. So again, let's say this is 1, that is 2, that is the rectangular, or if that is a triangular, then that is a triangular, or trapezoid, and that is a trapezoid. So simply the area of the load is the change in velocity. So now, again, velocity, the magnitude of the velocity on the shear diagram, the magnitude of the shear diagram is the slope of the moment diagram at a certain point, or that is the first derivative, okay, of the equation. So that you will not be confused. If we are referring to the diagram, okay, the value of the shear on the shear diagram on the certain point is the slope on the moment diagram at that certain point. Okay, slope. If you say slope, that is again the slope of the line. If that is a curve, then that is the slope of a line passing at that point. Then again, the change in the moment from the first point to the second point is just the area of the shear diagram. Okay. Now, okay, but the other thing here is that if you have the equation of the moment diagram, get the first derivative. For example, let's say that is this is uniform from A to B. Let's say that is B. So what does that mean? There will be a single equation of moment here, and then if I want, let's say I want to get the equation of the shear, then that is just the first derivative. Actually, we did that by summation of forces, summation of moment, to establish the shear and moment separately, but actually they are related. Okay, once you have the moment, you can differentiate that one, you will end up with the shear equation. Or the other way, once you have the shear equation, you can integrate that one to have the moment equation. Okay. Now, relating your load and your shear, the value of the load, the intensity of the load, is the slope of the shear. Okay, that is the slope of your shear. And then, of course, the change in the shear is the area of the load within the point that we are considering. Okay, so these are now the relationships. Okay, this is just to what we call this one, outline what we discussed a while ago. Okay, and so with this. Okay. So now, since we are referring to slopes here, we should recall our topics before on your previous subjects about slope, wherein a positive slope is going up and then a negative slope is going down. Okay, the bigger the slope, it means the steeper the line that we are referring to. Okay, so same thing, even if that is a bigger negative value means steeper, but that is just going down from left to right. Okay, we are moving from left to right. So it will be rising from left to right, if that is positive. It will fall from left to right if that is a negative. Okay. Now, point of zero shear and moment. Okay, this is now the point of zero shear and moment. Let's discuss about this before we will try to apply all of this into a problem. Okay, so shear and moment diagrams are merely the graphical visualization of the shear and moment equation. Okay, this is what I've explained a while ago. Okay, you can read about this. So, okay, discontinuities in the shear diagram are joined by a vertical line drawn up and down to represent the abrupt change in shear. Okay, I will explain that also in the example. And then, of course, a final point to be observed is the time. This time is that the highest and lowest point on the moment diagram always correspond to the section of zero shear. Okay, so this is important. The highest or the lowest point on the moment diagram is actually the same point where we can find the zero shear. Okay, so that is the importance of your zero shear. Where we will find the maximum and the minimum moment, you can find that one within the zero shear. If you can locate the zero shear and that is where you will find the maximum moment and maximum or minimum moment. Okay, how will that help us? Okay, if we will try to establish or analyze a certain beam, later on we will be dealing with, we will try to design this beam, and we want to know the maximum values that that beam is handling, maximum values of moment or shear that we are designing within that certain beam. Then these are what we need, the maximum moment or maximum shear. So we need to locate that one. Okay, so the value of x making m maximum can be found by differentiating your m with respect to x and equating the result to 0. Okay, so the question there is how we will find the maximum, okay, value of x making the maximum m. How will we find the maximum m? Okay, or how will we find that zero shear? So that is actually now using your differential calculus, the concept of your maxima minima. Isn't it that your shear, okay, shear is the slope of moment. Okay, so how are we going to find this zero shear? Of course, zero shear, there you can see that one on the figure itself, but of course later on we need to calculate the distances. But the question there is how we are going to find this one. Okay, so the value of x making m maximum can be found by differentiating m with respect to x and then equating the result to 0. That is maximize, okay, maximize or minimizing, maxima minima. You have equation of m, differentiate that one with respect to x. What is that? That is the slope. Okay. Differentiating m with respect to x is a slope. First derivative is slope. Equating your slope to 0 is getting the point on the curve wherein the slope has a tangent which is horizontal. So where we can find that tangent of horizontal, again, maxima minima, is the maximum and minimum points. Okay, we can recall that one on the figure. This result will be the shear equation V. Thus, we see that the maximum moment corresponds to the section of zero shear. Okay, we will look at that later on. So where the beam changes its shape from the concave up to concave down, we have what is called the point of inflection. Okay, if we will now try to trace the formation of the beam, isn't it, if we will try to exaggerate the formation of the beam, it can concave this way, a lot of concavity. So there is a section of that beam wherein that is opening downward. There is a section of that beam that is opening upward. If your loading is a little bit complicated. So the question there, where are we going to find that change in concavity? You discussed that one in your calculus. Is, okay, that is your zero moment. Okay, the beam changes its shape from concave up to concave down. That is what we call the point of inflection, and that corresponds to the section of zero bending moment. So the zero shear, that what is the value, or what is the what to call this one? What is the significance of your zero shear? That is where we can find the maximum or minimum moment. How about the zero moment? That is where we can find the point of inflection, the change of concavity of the beam, the deformation of the beam. Okay, its position may be calculated by letting the m equation equate to 0 or equal to 0 and then solve for the value of x. Okay, so that is what we will be applying, okay, for in drawing our shear and moment diagram. Okay, so let's try to have an examples, but first, okay, let's try to have a summary for the steps that we are going to do. So first and for all, we will first be solving the reactions, of course, and then compute for the values of shear and then the change at the change of load points, or that is the point A, B, C, D on our figure. We will try to calculate the shear and then the moments there, or the shear first, and then of course change the calculate the change in shear. Okay, how to calculate the shear? Of course, summation of forces vertical, and then calculating that change in shear from the first point moving to the next point. What is that amount of shear, or the change in the shear within that 2 points? Is the area of the load, isn't it? That is what we derived a while ago. And then now sketch the diagram, determine the shape of the W, okay, by differentiating your V. The intensity of the load ordinate equals the slope of the corresponding ordinate of the shear diagram. Okay, and then locate the points of zero shear. Okay, we need that one for us to establish the maximum and then the minimum moment. And then once we have that, okay, compute now the bending moment on the points of ABCD, or the points of change in loading, okay? And then of course at the same time calculate the moment at the zero shear, that is your maximum or minimum moment. And then of course using summation of moment on the left side or the right side of the figure. And then we need to change the we need to calculate the change in moment by getting the area of the shear diagram between these 2 points that we are considering. And then now we are going to sketch that one. Okay, once we sketch that one, and then of course we are going to connect these points, then all we need to do is find if ever we have there the change in, the inflection point. All we need to do is equate the moment into 0 and then solve for x. Okay, so the shape, sketch the moment diagram to the ordinates of the bending moments computed in step 5. The shape of the diagram is determined by your V. Okay, the slope of the diagram, a moment diagram, is the intensity of V. Just like here, the slope of the, for us to know, will that be going up or down, or is that opening? If that is a curve, is that concaving downward or concaving upward? We will know that one. If in shear, if we are drawing the shear, we will know that slope by the intensity of the loading at that point. If that is in moment, we will know the slope by the intensity in the shear diagram. Okay, so slope at the corresponding ordinate of the moment diagram. Okay, so that is the steps that we are going to follow for us to draw the shear and moment diagram. Okay, and we will be doing this by 2 methods, using the equation and then by drawing alone. Okay, by semi-graphical method. So let's have this example. Consider the given loaded beam below, draw the shear and moment diagrams, and determine the locations of the point of zero shear and point of inflection. Okay, A, using the shear and moment equations. So that is what we are going to do first, using the equation. We will first establish the equation before we will draw, just like what we did in Unit 1. But this time, I will now be explaining how to connect these points. Okay, and then second is draw or do the same thing, but this time using the relationship of the load, shear, and moment. And that is what we call the semi-graphical method. Okay. Okay, so first solve for the reaction. That is the first step. So let's say take a moment at B. Take a moment at B. So on this side, okay, let's say clockwise is positive. Okay, clockwise is positive. This side will be a counterclockwise. Okay, this will be a counterclockwise. The loading here, and the loading here, the part of that UDL on this side will be clockwise, so positive. And then we have here 8 kilonewtons, a concentrated load clockwise. And then we have here this unknown. This is still unknown. That is what we are going to solve first. dB, that is a counterclockwise. Okay. Or simply, if that is what you can do here, you can divide these two. Or simply, you can actually consider this as a single. In the solution here, I consider this one as a single. So compute the equivalent of this. So 2 times the distance, what is that? 9 plus 3 is 12. So 2 times 12. So where is the concentrated load located? At the middle of that. So 12 divided by 2. 9 plus 3 is 12 divided by 2 is 6. Minus 3. Okay, so if that is 6, so somewhere here, minus 3. So that is the moment arm. So that will be a clockwise. Okay, that is a clockwise. So again, the concentrated equivalent of this is somewhere here in the middle, and that is located at a 3, distance 3 from your point B, where we are getting the summation of moment, and that will make it clockwise. So the intensity is 2 times the length, which is 12, and then this is the center, which is the half of that is 6, minus the 3, that is the moment arm, which is also 3. And then this one will be still a clockwise, 8 times 9. Okay, moment arm is 9. And then your unknown dB counterclockwise, which is at a moment distance of 9 times 3, or 9 plus 3 is 12. Simply solving for dB is equal to 12 kilonewtons. Okay. And then you can do summation of moment at E. Do the same. You will end up with dB is 20. And then you can check summation of vertical. So 20 plus 12 is 22. So if I will multiply this to get the equivalent force, so 2 times 12 is 24. So this is 32. 12 plus 20 is 32. This will be 9 times 2. 12 times 2 is 24 plus 8. 24 plus 8 is 32 equals this, the reaction. So that is correct. Okay, now let's try to establish the equation. Since we will first use the in A, we will first use the shear moment equations. So cut at A, okay, the leftmost part, A, that is our reference point. So every X will be coming from that point A. So cut here at AB, cut. Then you will expose there a shear, which is, we have here a force equivalent of that is W, which is 2, times the distance. If I will cut that, that is a distance X. So your shear is negative 2X. That is our equation here. And then later on we will be solving. So we will be solving the equivalent of shear at A and B. Okay, substitute the distances. Okay. So at X equals 0, that is 0. At X equals 3, that will be a negative 6. Okay, so this is our shear and at A and B. Now the moment, take a moment at the section where I cut that one at a distance X from A. This UDL will be having a counterclockwise, which is a negative. 2X times the distance of that, which is half of the X, is X over 2. So you will end up there with a negative X squared. That is our moment equation at your member AB. Substitute X is 0, that is moment 0, which is true because that is a hanging, okay, that is a free end, so that should be 0 moment. And then substitute 3, that 3 here in our X, that will be a negative 9, that is our moment at B. Okay, now let's proceed to your BC. I will cut at BC. Okay, take a moment. I mean, first start with shear, so summation of shear, going up is positive, so that is 20 positive, and then down is 2 times negative 2 times X. Again, if I will cut here, the X will be up to that point, first point. Okay, so negative, since that is going down, and 20 is positive, so going up. So that is our equation. Substitute 3, that is at B. 3, you will end up here with 14. Substitute 12, which is at your point C. 9 plus 3 is 12. Substitute that in our equation, you will have negative 4. And then take a moment at that section. So take a moment. 20 is a clockwise moment at the section I will be considering here. So that is 20. But the question there, what is the distance? If I will cut that is X from A, what is the distance of this 20? That is X minus 3. And that is positive. And then do not forget your moment of this UDL. So the value of that is negative 2X. Since again counterclockwise is a negative moment, 2X times the moment arm, half of X is X over 2. Simplify is negative X squared, and then plus 20 times X minus 3. Substitute the values. Okay, at B, X is 3, that is negative 9. At C is 12, that is positive 36. So these are your moments at B to C. Okay, now let's go to the last section, or the last segment, CD, cut. Take a summation of forces. So going up is 20 positive. Okay, you can now consider the entire UDL, which is 2 times 12. Okay, 9 plus 3 is 12. That is negative going down. And then do not forget your 8, that is going down. So that is a constant from C to D. Okay, it means it is not affected by a distance. So constant from C to D of negative 12. So C is negative 12, D is negative 12. Take a moment. Okay, so again, this one, we will now be considering the entire, since that is now terminated at C. So that will be a counterclockwise and negative. 2 times 12, 3 plus 9 is 12. And then the distance of that is located at, okay, X is up to the section I cut here, but that length of UDL is just 12. So let's say that is the middle. So what is that? The middle of 12 is 6. Okay, the middle of 12 here is 6. And then X is up to that A. So somewhere here, the distance of that center to that point here where I cut is X minus 6. Okay, half of that 9. So that's why this one, 12 divided by 2, that is 6. Okay, and now your 20 will be, okay, cut there, 20 times X minus 3. Positive, since that is a clockwise, and then another negative 8 times X minus 12. Okay, somewhere there, this is 12, so X minus 12. So now simplifying, we have this, substitute at X equals 12, that is your C, 36. At X equals 15, that is your D, you have there 0, which is true since that is simple support, so there should be no moment. Okay, all we need to do now is, okay, find your point of zero shear. Okay, how are we going to do that? is using your equation. Since we are using the equation, okay, so how are we going to find the zero shear? So these are your equations, okay, shear equations. That is for AB, that is for our BC, that is for CD. All we need to do is equate to 0 since we are finding the zero shear. So equate your first shear equation at AB, x will be 0. Well, that means zero shear at the first point. Of course, since that is the starting point. So we will not have there a zero shear. Of course, again, the x equals 0, there is a zero shear, but that is the starting point. So of course, we will not consider that. What we are finding is a zero shear in between. Okay, zero shear in between. Now on the segment BC, let's find if there is a zero shear. Equate that to 0. You can actually now calculate as x equals 10. You have now a value of x. It means that from A, which is 10 meters from A, that is a zero shear which will be found between your BC, which is actually 10 is there. Yes, yeah. This is 3, and then what do we need to complete the 10 is 7. So somewhere here, okay. So that is where we will find the zero shear. And what is that zero shear? That is where we will find the maximum moment. Okay, maximum or the minimum moment. It depends. If that is a positive moment, then maximum. If that is a negative, then minimum. Next, there is to solve for the points of zero moment. So that is your point of inflection. I will explain that one later, point of inflection. So equate the moment to 0. So we only have these moments here, 3, 1, 2, 3. So first, equate this to 0. Moment at AB. You will have there x equals 0, which is, yes, that is true. Moment is 0 at A. But of course, we do not need that. Since again, we are finding the zero moment and zero shear within the length, not on the endpoints. We will expect a zero shear and zero moment on the endpoint since, of course, that is equilibrium. Okay, so now we can neglect about that, x equals 0. So, of course, we will neglect about that. Now, let's go on the BC. This is your equation. Equate that one to 0. You have here x squared. It means there are two values of x. You have here 3.675 and then 16.325. But looking at x, which is 16.325, isn't it 16? That is more than the distance since our beam is 9 plus 6 is 15. Our beam is only 15 meters and that is according to the value of x is 16. That is outside the beam, of course. That is to be neglected. So, how about the 3? That is within. So, okay. We can find an inflection point or zero moment at a point 3.675. Or that is just after your point B going here. Okay, just after that is close to your point B. And then, lastly in your CD, equate that one to 0. You will end up with, equate this one to 0. You will end up with x, which is 15. And that is true. That should be 0 since that is the last point. So we will not consider that one since that is the end point. So we will only have one zero shear at x equals 10. That is where we will find the maximum moment. And one zero moment at x 3.675, which is the inflection point. Change of concavity on the deformation. Okay, now we are ready to draw. Okay, so these are your shear equations. Okay, now isn't it that we established a relationship between the moment and then the shear equation, wherein the first derivative of the moment is the moment equation is the shear equation, isn't it? So look at this, differentiate with respect to x. That will be 2, negative 2x. That is your shear, isn't it? In here, okay, simplify this first. Simplify this. This will be positive 2x. This will be negative 60. But differentiating that one, the constant will be eliminated. This will be negative 2x. 20x will be 20. So we are good. The same thing with this. Simplify. So negative 24x, 20x, and then 8x. That will give us negative 12x. Okay. 20 minus 24 minus 8. So this will be negative 32 plus 20 is a negative 12x. Differentiate that one is 12. This will end up with a constant, okay? That will be constant, this will be constant, this will be constant. Even if you will solve that one, differentiating a constant is 0. So, it is true that the first derivative of the moment equation is the shear equation. Or the reverse, you can integrate, okay? Now solving for the value of the moment at the point of zero shear. Okay, we established now your zero shear to be found at x equals 10, which is at BC. Now using the moment equation at BC, okay, moment equation at BC, this one, using this, since again we established that from your VBC, x equals 10, substitute that x at your MBC, okay, substitute that, you will end up with the value of the moment at x equals 10 to be 40. So that is the maximum. Now we are ready. Now we are ready to plot this one. Okay. So we already know that plot your first point. Okay, we established that one a while ago. These are the values. We have here. Let's start with the shear. 0, negative 6, 0, negative 6, and then 14, negative 4, and then what's that? Negative 12, and then negative 12. Okay, so that is what we are going to plot in your shear diagram. So 0, negative 6, and then there's a change. Okay, this is now what we are talking about, the abrupt change. There will be abrupt change. If people say abrupt change, it is a change in shear at a single point due to concentrated loads. It could be a reaction or a concentrated loading. Okay, concentrated forces. So again, 0, negative 6, and then that will change abruptly. It will go to 14, isn't it? Again, these are the values. If I will substitute here at x equals 0, you will have here a 0. Substitute at x equals 3. You will have here negative 6, which is true. Now let's go to BC. Using your shear of BC, substitute 3. If that is 3, that is negative 6, that will become positive 14. So that's it. At the same point, you have two different values, just like in our unit 1. But this time, I am now explaining the reason. Why there is a change, okay? That is due to the concentrated force, which is the reaction. And then now going to C, substitute there your 3 plus 9 is 12. That is 12 times negative 2 is negative 24 plus 20 is negative 4. It is a negative, it is below. Then there is abrupt change again. Why? Because there is a concentrated force, which is 8 negative going down. So negative 4 minus 8 is negative 12. And then that is constant because of course negative 12 constant. And then the same thing. And then suddenly it will go back to 0. Okay, this will always close. Okay, your shear and moment diagram should always close, unless, okay, in your shear that should always close, but in your moment that will only be open, okay, or that will always close. That will always close in your last point because we are satisfying the equilibrium. Okay, so again, now we plotted these points. Now all we need to connect. So the question there is why is it a straight line? Okay, why is it a straight line? Okay, why is this slanted and why is that a constant? Okay, so this is now using the relationship. Isn't it that the slope on your shear is the intensity of the loading, okay, or the value of the loading? So this one, the slope of this is a negative going because the line is going down. At any point here, the line is going down. That's why this is a straight line going down. Since your loading at any point in your AB is a negative going down. So that is a negative line, straight line. And then, or again, this is first degree. Isn't it? Going back there is the derivative of moment is shear. The derivative of shear is loading. What does that mean? If we are differentiating, we are trying to reduce the degree of the equation. So look at this. It is a flat, or it is a constant, or it is a horizontal. It will now become a first degree line. Okay, if you say first degree line, your equation will have x, okay, which is raised to 1. And then you will end up with a curve. This is actually now a second degree. It is now a parabola. Okay, so that is the succession of your equations. 0, it will become first degree, second degree. So if we started with a concentrated load, this will be flat or a constant and then first degree. Or if we started here with a second degree loading, that will be a third degree, fourth degree. That is the succession. Okay. Now how to connect this? Okay, that will now be a straight line going up abruptly, and then how is that the straight line? The same thing, the same reason. Your loading here is -2, which is constant, therefore that is a straight line going down. Slope is going down. And again, if you will try to get a slope, isn't it? Rise over run. The rise here is -6, the run is 3. So -6 divided by 3 is your loading, which is your slope. Same thing here. Do the same thing here. That is 9. Is this 9? Yes, this is 9. And that value is 14. And this is, what do you call this one? 14 plus 4 is 18. So 18 divided by 9 is -2. Negative 18 divided by 9 is -2. The slope is -2. Okay? So that is a straight line. Again, this is flat. It will go first degree. And then second here, there is no loading here. There is no loading. So that will be flat. And then next will be first degree. Okay. So how do you know that that is constant? Again, there is no loading. So the shear here is constant. So that is how to draw your shear and moment diagram. How to know if that is a straight line, a curve, or that is going up, going down. Okay. So again, that is going down. So slope is negative, going down. Slope is negative, going down. Now let's proceed with the moment diagram. Isn't it? We solve your zero shear, that is at x equals 10. So 3 plus 7, somewhere here is 7. So the remaining here is 2 meters. So that is 10. Okay, that is x equals 10 up to the zero shear. And the moment there is 40. So now, plot your moments. 0 at A. So need to establish that one. At x equals 0, in here is 0. At x equals 3, that is -9. Okay, you have here your -9. And then again, we establish that as the maximum. And then substituting here to get your moment at C. Okay, by the way, look at this. If you did not establish that this is a maximum, and you will calculate the moment there at 36 to be 36, substitute your 12 in your equation here is 36. You might be thinking of connecting that one as a curve, and then this will be the highest point, which is wrong. Because according to the figure here, zero shear is the maximum. So let's try to calculate. And we prove that that is 40, which is bigger than 36. So your curve will be passing through that. Okay, so this is a higher point. Okay, so this is now a maximum point. Okay, zero shear. And then that is 36 again, substituting at x equals 12 in your equation here, that is 36. And then substituting 12 also in your CD will be still 36. We solved that one a while ago. Okay, MC is 36, MC is 36. Okay, so that's it. And then lastly, 0 at D. So now the question there is how to connect if that is going up or going down. So again, that's it. The slope here, the slope of the moment is the intensity of the shear, just like here. The slope of the shear is the intensity of loading. The slope of the moment is intensity of shear. Okay, so the values here is negative. The values of shear in these points from A to B is negative. So what does that mean? Isn't it that value at A is 0? So what is the line with a slope of 0? It is a straight line. So the tangent here is a straight line. Now at this -6, so the slope is a -6. At this point, the slope is negative. So connecting that one, that will be a curve. Okay, how do we know that that is a curve again? From a straight line plus 1 degree, it will be a curve. Okay, first degree, it will now become a second degree, which is a parabola. And how do you know that that is opening downwards? Isn't it? It could be curved, but it could be opening upward. No, because look at this, negative, 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 negative. So your tangents are all negative. Negative, 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 negative. So connecting that ones will give us this curve concaving downwards. Okay, so just like considering here points, the tangent are all negative, decreasing up to your point at B. Okay, the negative slope is not decreasing. From 0, it will be a negative slope increasing up to -6. That is the slope. That's why it will be opening downward. Okay, Now from your point B going to that maximum, now your slope here, the intensity of loading here is now positive. Okay, positive, positive, positive. But from a big positive 14 to, it will be going to 0. So again, what is 0? That is a slope of horizontal line. So the line tangent to this point here is horizontal. That's why it is a maximum point on the curve. So look at this, a big slope. So a sharper slope. If I will try to draw a tangent line here that is steep, and then as I go near your maximum point, the slope is now decreasing, so it will now be lower, and then connecting that one up to the time it will become flat. Okay, the tangents here will be steep, it will become smaller up to the time it will become a flat line up to your maximum point. And then lastly here, okay, that is from 0 it will be a negative, just like this. 0 it will become a negative, 0 it will become negative, so opening downwards. And then lastly, this is just a straight line, so it will become a straight line but inclined. Slope is a negative since the values here are negative. Okay, so that's it again. How do you know this is a curve? Since these are first degree equation of line, or that is an inclined line. A straight line here, a straight line, it will become inclined line, first degree, it will become a curve, second degree. Okay, a flat here, it will become inclined line, it will become a curve. In here, no degree at all, this is a flat, and then it will become a first degree. Okay, so that is the succession. So now we have your shear and moment diagram. We can now go back to your unit 1 and explain why the connections are curved and then line. Okay, so let's now draw using a semi-graphical. So without passing or without establishing, let's forget about the equation. All we need to do is solve the reaction, maximum shear, and then plot this one and connect. Okay, so again, we established the reactions a while ago. That's it. These are our reactions. And then all we need to do is solve for the shear and then solve for the change in the shear. So that's what we are going to do. So let's start at A. The shear there is 0. I will cut at the very first point. There is no force, so that is 0. The shear at your A is 0. If I will now try, okay, look at this. Isn't it that the change in shear from A to B is the area of the loading from A to B? So what is the area? That is length times the UDL, or that is a rectangular. If I will cut at B, that is a rectangular loading, which is an area of 3 times your intensity 2. So that is 6. But it is going down. So from 0, the change is negative 6. So 0, look at this, negative 6. Okay, that is change. So the negative 6 or 0 plus negative 6, you will give us negative 6 shear at B. Now again, how do we end up with 14 there? Because there is a concentrated load going up. So we will add that one. Going up is positive. From negative 6 plus 20, it will be a positive 14. Okay, so we are good with that. And then, how about from 14? How do we go to C? The change in shear is again the area of the loading. We have an area here. The length times height, since that is a rectangle. So 9 times 2 is 18. Okay, let's go here. Okay, 9 times negative 2. Negative because it is going down. Okay, so 9 times negative 2 is negative 18. That is the area of the loading. So that is the change of shear from your from B to C. So we have here 14 plus negative 18 will be negative 4. So that will be flat there below what you see. And then again, there is an abrupt change because of this concentrated force which is going down. So negative 4 minus 8 is negative 12. And then lastly, is there an area of loading here? None. So that will be constant. We will carry that there. And then that will be closed by your reaction here, which is positive 12. It will be going back to 0. Okay? That is how you will know you are correct, because it will always close on your last point. All we need to do is connect this one. And again, the same explanation as a while ago. This is a straight line. It will go plus 1 degree. It will be a slanting line. Okay? Since that is a negative, the slope will be going down. and then of course we will connect that one because of the abrupt change, and then again negative, which is flat, it will go inclined line going to 4, negative 4. Do not forget about that. That is what we established a while ago. Before that abrupt change, which is 8, we will connect that one. There is no change, connect, and then lastly we will close. So that is what we will be doing here. Okay, going down, up, down, down, constant, and then up. Okay, so again, do not forget about that. Positive is going up, negative is going down. Okay, the slope is the intensity of loading. So negative, since the slope is going down, or the values are going down, the loadings are going down. So that's it. Now let's proceed with your moment diagram. Okay, moment diagram. But first, again, before we'll do that, since we can see here there is a zero shear, so we need to solve that one. So again, forget about the equation since we are using a semi-graphical or simply a graphical. So let's say we do not know the equation. So how are we going to solve that? By graphical or by geometry, of course. Look at this. This is a triangle. If I will try to extend that one up to that point C here, negative 4, that is also a triangle with the same slope. Okay? A triangle with the same angle. This triangle here and the triangle on top. So using ratio and proportion, okay, by ratio and proportion, the height of this small triangle on top, 14, and the length of that, which is the unknown x. Let's try to get that as the x. The distance of the zero shear to B. Let's say that is x. So 14, height of that, 14 is 2x. And then if I will consider the big triangle going down to that negative 4, the height of that will be 4. We have here that 4 here. Okay, forget about the negative. We are referring here to dimension of a triangle. So we have here a 4 going to that beam, and then another 14. So 4 plus 14 is to the distance. What is the distance? This is entirely 9. From B to C is a 9 meter. So 14 is to x is equal to 14 plus 4 is to 9. Calculating your x will give us x equals 7. So in this one, our x is from B. Therefore, your zero shear is 7 from B. Or if you will try to recon that one from A, add your 3. So x is equal to 10 meters from A, which is the same using our equation a while ago. Okay? Now, all we need to do is remember that zero shear is the maximum moment. We can now proceed with moment. Okay, how are we going to draw the moment? The same thing, just like what we did in shear. Calculate the moments in this one, we calculate the values by referring to your loading. In your moment, we will now calculate the moments referring to your shear. Isn't it? The change in the moment is the area of the shear. The change in the shear is the area of the loading. Okay. So let's start here. What is the moment at your point A? There is no moment load at A, so of course that is 0. But if there is a moment load, just like your example number, I guess that is example number 4 in your unit 1, you have there a moment load on the endpoint, you need to consider that. But since we do not have that, automatically your moment at that point is 0. Okay, that is 0. Now, solving for the change in moment from A to B, that is the area of the shear diagram, isn't it? So why is it negative? The question is, why is it negative? Because that is below. Okay, this is your neutral, or this is your 0. So going up, or that is on the top, is positive, down is below. So always the same thing with the area. On top is positive, area is below is negative. The question there you might be asking, sir, why is it that is on top? Your loading is on top of the beam. It's okay. But why is it negative? Because of course your loading is going down. So that is the only difference here. Loading in the shear. If you are solving the area on the loading, consider the direction of the loading. But if you are solving the area on the shear, just consider the location. This is below, so that's a negative area. This is positive area, negative area, negative area. Okay? And look at this. Your dimensions is negative here. That is a positive. So therefore, you will be ending up with positive area on top, negative below. So change of moment from A to B, area of this is a triangle. Okay, 1/2 base times height. So area of that change in your moment is 1/2. Base is 3 times height is -6, will be a -9 area. So from 0 it will be a -9 moment. Okay. Now, there is no moment here. But if there is a moment, concentrated moment, there is a sudden change or abrupt change of moment. But since we do not have moments within this one, okay, but in case there is a moment within these points, there will be abrupt change of moment, just like in shear, okay. There is abrupt change of shear since there is a concentrated force. There will be an abrupt change of moment if there is also concentrated moment, but there is none, so there is no abrupt change, okay. So now all we need to do is from this -9 find the change in moment. But of course, do not forget, consider the moment here, okay. Consider the moment at the zero shear. Okay, how do you know that that is 40? How do we know that this is 40? How do we know that that is 40? Okay, know the distance. This is 7. We established that one a while ago. We solved the zero shear. So all you need to do is find the area of this. This is a positive triangle. So 1/2 base times height. 1/2 base is 7 times height is 14 is positive 49. So from -9 plus 49 will give us 40. Okay, isn't it the same as how we ended up a while ago using the equations? And then do not forget, this is now positive 40. There is a negative area. So 1/2 base times height, that is just a triangle. 1/2 base times height, it is just a triangle. So calculate that one. This will be a -4. So 40 minus 4 is 36. And then finally, the area here is a negative. Okay, this is now a rectangle. Base times height. Okay, base times height is 3 times height, which is negative, is -36. So from 36 minus 30 minus negative or plus -36 will give us 0, which is true since that should be 0, since there is no moment here. Okay, so all we need to do now is connect. Okay, connect. Recall again, slope is going up, positive slope, negative is going down, and then the slope of the moment diagram is the value of the shear. Okay, so the slope at that point is 0, since that is 0. So we have here a straight line. The slope there is -6. So it is a -6 going down. It is a line in your point here going down. So if I will connect that one, you will have this. Okay. Again, from 0, that is a flat line, to a -6. Your slope is -6, so that is a line going down. And connect that one slowly, and then you will end up with a curve. Why is it again not going up, not concaving up? The explanation again is here. You can read about that, but I already explained it already. Okay, same thing here. Okay, from the slope here, which is positive 14, it is now a steep slope going up. Steep, since that is a big slope. And then the slope at that zero shear is 0. Okay, 0, so flat. So from steep going slowly, since again, why is it? This is changing, the slope is changing slowly. So the same, from 0 it will change slowly to -6. So it will be going that way. And here is 14, it will be changing slowly going to 0. The slope is changing slowly to 0. So that will curve going that way. And then from 0 it will -4, the same as that. It will slowly be going down. And then same thing here, but this is, of course, look at this, this is a flat line, so it will just be an inclined line. Okay, directly go down. So that is our shear and moment diagram. But lastly, okay, your point of inflection. Isn't it? Compare this one a while ago using the equation, the same. But this time, okay, find your point of inflection. Point of inflection is actually, that is the change of concavity. I will explain that one later on. But as you can see, where is the zero shear? You can find it here. I mean zero moment, you can find it there. We solved using the equation a while ago, that is 3.675. That is just after, that is just after B. Which is, if we will try to magnify, let's try to zoom this part. This is this drawing here. This is your B here, that is just the zero moment, just after B. So that's why your value a while ago using the equation is 3.675. But let's forget that we know that one. All we need to do is calculate. Okay, calculate that one. This is by ratio and proportion using the square property of parabola. Okay, this is square property of parabola. If you say in your triangular, solving for that 7 here is by ratio and proportion. Look at that. Where's that? Here, x. Solving for that x is ratio and proportion, since that is a straight line. But we will now go on the second degree of equation. Second degree na tayo. So we will now be on second degree already. So we cannot just use their plainly ratio and proportion. We will be using the squared property of parabola. Just like the same as ratio and proportion, only that, isn't it, in your parabola, there are two values of x in a one value of y. Okay? This is your parabola. In a certain value of y, let's say this is a value of y, there are two values of x, two values of x, two values of x. So there are two values of x in a value of y. So that is how we will apply the ratio and proportion. If we are ratioing x with y, we will always square the x. Okay? So look at this. If I will try to indicate here, okay, this is, let's say this is your first point here, that distance up to this maximum, okay, distance up to this maximum, let's say that is x2, okay, horizontal, and vertical is y2, okay, y2. So x2, do not forget again, squared, always square your x, since that is the squared in our parabola. So x squared is 2y2. So x2 squared is 2y2 squared. And then in this point to that point, okay, let's try to do the same. Let's say that is now x1 and this is your y1. So the same thing, apply the square in your x. So x1 squared is 2y1. And then play around with this, okay? What are the values? We know some of the values here, just like y1, we know that one to be 40, isn't it? You can see it here, that is 40. And then what else do we know? The distance from your B to E, which is 7, isn't it? B to E is 7. That is your x2. X2 is 7. And do not forget your y2 here, okay? We know that your y1 is 40. All we need to do is add this part here, which is a negative 9, or that is 9, since we are referring to a distance. So 40 plus 9. Ratio and proportion, you will end up with x1, which is 6.325. 6.325 or 3. I'm sorry, I think this is wait, let me just check. 6.325 x1. Okay, yes, that is our x1. Okay, sorry, the distance that we established a while ago is from A. Now that is that x1, we, since in our figure here, that is from E. X1 is from E. So going back there, if that is the 6.325 from E to that point of 0 moment, then what is that distance going to A? So all we need to do is 7 plus 3, that is from A to E. Subtract your distance that we solved, your x1. Okay, subtract that 6.325. You will end up with distance from A going to that 0 moment as 3.675, which is the same as a while ago using the equations. Okay, so now we have points here. Look at this. Let's just exaggerate. Let's say after I load this beam, I will apply now the loading. The beam will of course deform. So let's say this is the deformation. Okay, look at the loading. So there is the loading here, but because of the loading, this will go up, since that is not supported at A. So maybe that will do this way, and it will bend because it is loaded all throughout AB. And then this will bend going down, going up. Okay, bend going up, and then it will deflect down because of the loading applied here. Isn't it? We have a loading applied there. And then we established that the maximum moment is found at your E, which is this, which is a 10 meters from A. So that is the lowest point. Okay, that is the maximum moment is where you will find the lowest point. If you will have the minimum, or this one here, or let's say this is on the other side, this is below, that is a negative, this just means that is on top, or that will become a highest point. Okay, so where you will find the maximum moment, that is where you will find the lowest point on the deformed shape. If you will try to draw the deform of the beam. By the way, for you to relate the deformation, okay, that is the deformation of the beam with the moment diagram, it will just be the mirror. Okay, look at this. This is your moment. So that is the deformation on top. Deformation. Okay. This is the moment. So that will be the deformation. It is just a reflection, okay, the opposite. Okay, so now that point here is the point of inflection. Why do we call it point of inflection? It is the change of curvature. Why? Look at the deformation here. That is opening downwards. See it? Opening downwards, and now it will be opening upwards. So the concavity from downwards to upwards, there is a change of concavity. That is what we call the point of inflection, and you will find that one at the zero shear. It is not exactly at the support, okay? It will be there at 3.675. So that is your shear and moment diagram, okay? So again, this is just a recall, or this is now just a summary. We already summarized using your equation, isn't it? Establish your shear equation, moment equation, substitute the points, okay? And I already discussed how to connect these points, okay? Relating it on the relationship of the load, shear, and the moment. Now, if you do not want, or if the problem will not require you to be establishing the equations, all you need to do is draw directly the diagram. Then you will be doing the semi-graphical. All you need to do is, if you want to draw the shear diagram, base that one on the loading, okay? Base the loading. If you want to get the shear here, that is, cut there, get the shear. If you want to get the shear at B, cut that one, and then summate forces, then that is the shear, okay? And then same thing here. How do you find? Cut, and then you will get that one. And of course, the same thing, the area of the loading is the change. So if there is no loading here, or there is no area of loading here, then there will be no change. That will be constant. But since there are area, just like this, there are area of loading, so there is a change in shear. While in here, there is no area, so there is no change. That is constant. And then look at this. That is a first degree. If you are using the equations, isn't it? Look at this, first degree. First degree, this is a constant or horizontal line. There is no degree. So first degree, 0 degree of line. So going to your from loading that is flat, it will go first degree. Flat, it will go first degree. No line at all, so it will start with a horizontal line. Okay. Now from your shear diagram, first degree, it will now become a second degree based on the equations. So you can prove that one using the equation. First degree, it will go second degree, and then horizontal, it will go first degree line. Okay, straight line, inclined. What is the difference of N0 and N1? N0 is still a straight line, but that is a horizontal. N1 is a first degree line, which is inclined. Okay, inclined line. Okay, that's it. That is how we will summarize the shear and moment. Okay, shear and moment equations, and then diagram. So if you have any question, you can comment below the video, or we will be discussing that on the next live meeting. So thank you very much for watching.